classes, we have talked about networks, we have talked about local area networks, and we have explained how they operate. Now, local area networks are interconnected to create what we call metropolitan area networks and the large area networks and so on. So, why do we need the interconnection of lands or the interconnection of local area networks? One is the limited amount of supportable traffic. That is one of the reasons. In a local area network, there is not so much traffic. So you need to control how this traffic comes into your network and how it leaves into from your network. The other one is limited length or cable distance. If you are using cables, cables can run up to 100 meters, or if you are using fiber optic, then it is okay. But these other cables, they go 100 meters, 200 meters, 300 meters. And then you are going to have a problem of distance, or what we call attenuation. So that is why if you are talking about limited length, then you need to have interconnecting devices. Also, creating of collision domains. If you create a very large local area network, then we are going to have many collisions. So in order to reduce the collisions, then we can create several LANs which can now be able to work properly. And then the limited number of stations which can be allowed in any local area network. So those are the reasons why we have the interconnection of networks. So in order to have these interconnections, we need different devices. And these devices work at different layers. If we have a device like a hub, it works at the physical layer. And we say they are essentially repeaters or signal regenerators, meaning that they will just receive a signal and they forward it. They don't have the capability to understand where this signal is coming from or where it is going to. They don't have that capacity. That is why we can call them what we call dumb devices, that they don't have any capability to know where this signal is going to or where it is coming from. They just receive and forward it. That is their work. So them being that simple, they have not sorted some of our challenges we are talking about here, like collision domains and having the now limited number of stations and length. What they are dealing with is the problem of length, but they are not talking about shared bandwidth or collision domains and number of stations. That is not their problem. That is why we say they are not enough. So what do we do? Okay, also repeaters are there. Hubs and repeaters, they are almost the same. What they do is to receive a signal, regenerate it, or give it strength to move ahead, and they forward it. But then these hubs, they just connect, but they do not isolate. That is the challenge with them. They do not isolate collision domains. A node may collide with any other node residing at any segment of that network. So they are simple, inexpensive, and that is all they do. But then we need better devices to deal with some of these limitations, like having several collision domains, and also making sure that these collision domains are also covering some extensible geographical location. So what do we use? We started using bridges. So that is the solution to hubs, the use of bridges. Uh, sorry. Sorry for that. Let us continue. So in order to solve some of the problems with hubs and repeaters, then bridges came about. A bridge is also a link layer device. Hubs and and repeaters, they work at the physical layer, which is at the electrical layer, cable layer. But here we are looking at the second layer of the OSI model, which we call the data link layer. And here we are having a device like a bridge. Now, a bridge is going to separate two local area networks. Like you can have devices on one local area network and other devices on another local area network. And then these two area networks are going to be connected by a bridge. Or you can have one local area network and then you divide it into 2 or 4, depending on the number of ports in that bridge, by using a bridge. So a bridge does what we call separation of collision domains, so that if a device, for example, this is the device. So if this is a device which is right here, and it wants to transmit to this device right here. When this signal is sent to the bridge will determine if this device is still in this subnetwork here. Then there is no need of forwarding that signal to the rest of these devices in these other segments. No, it will be contained here because the destination is within this segment. If this device wants to communicate with a device right here, then it is the work of the bridge to forward that signal to this network. So broadcast will be done up to here and not this area. That is how we separate the collision domains, and that is what a bridge does. So it uses the CSMA collision division, or what we call carrier sense multiple access with collision detection, to access a segment and transmit. So it will sense, where is this destination? If it is within my LAN, I don't need to forward this to the rest of these devices, because that is going to increase the possibility of collisions. So that is how a bridge works. The same is operated here. So a bridge has that capability of separating collision domains or separating local area networks. And they do frame filtering and forwarding. That is what I was explaining there, that if this data which is being transmitted is within the same LAN, then you do not need to forward to the other LANs. And how does it know how to forward? It will just broadcast to the destination LAN. It doesn't know the exact destination, so that is why it broadcasts to the destination LAN, not the destination node. So that is how it does. And it does that by learning which host can be reached within the interfaces which are available, and it does that using a filtering table entry. Still, that is not enough, and that is why we came to what we call switches. These are just differences between bridges and routers, which we will come to in a while. But let us look at switches, which are also operating at the layer 2. At the second layer, you find that we also have switches, but they are more intelligent than bridges. A bridge is just separating the local area networks, but it doesn't know the exact node where these packets are being sent. But now, a switch has an idea of the exact destination or the exact host to which these packets are being forwarded. So once if a device A wants to communicate with device B and A to B simultaneously, then a switch will forward this packet straight to B. It will not now broadcast to all these devices available on the network. No, it will just forward them to the exact destination, hence it removes collisions. So it is more intelligent in that the other devices were just broadcasting. Like a bridge is broadcasting to the entire LAN. So all the devices in this LAN, for example, let me just go back a little bit. What we are saying, if it is a bridge here, a packet which is being forwarded to this LAN here or to this node here is going to be broadcast to all the nodes. So these nodes, they will be just checking on the data packet, and if it is not the destination, it drops until it reaches the exact host. But now that is being compared with a switch, which now, instead of broadcasting or sending to everybody, it will just send or forward to the exact destination. So that is how a switch works. Now, there are two types of switches. There is what we call the cut-through, and there is another one which is called store and forward. When we are talking about cut-through switching, it is a bit faster and it is better in terms of speed, but it has a problem of error checking, because what it does, it forwards this frame or it forwards this packet before, once it reaches the destination, it will just forward before waiting for the entire packet to arrive and then forward. No, it will just read the header. It sees, oh, this is the destination, then it will forward. So this reduces the delay or what we call latency, but errors, it may forward a packet that has errors. That is the problem with the cut-through forwarding or the cut-through switching. But then there is the one we call store and forward, whereby the switch will have to receive the entire packet, check it, and then it forwards it towards the destination. It must be somewhere here. No, it is not there, but there are those two types, what we call cut through and then store and forward. So when you look at this switch here, it is able to connect so many local area networks, and then it forwards to the specific destination address. So it is an improvement of a hub, and they are used at the data link layer. They can interpret the address information. That is why we are saying they are more intelligent, and they resemble bridges and can be considered as multi-port bridges. So they are not going to be limited by bandwidth, because all these ports, they are going to be separated. If this switch has like, it has the capacity to transmit at 10 megabits per second, 10 Mbps, then each port is going to be 10 megabits per second, meaning that the bandwidth is being used better. Unlike when we compare it with a bridge, which then is going to, a bridge or a hub is going to separate that, or is going to divide that 10 megabits per second by the number of ports. That is another difference between a switch and a hub and a bridge. A hub, if a hub has like 10 ports and it is transmitting at 10 megabits per second, then that 10 megabits per second is going to be divided by 10, so that each port is transmitting at 1 megabits per second. Unlike a switch, whereby if it has 10 ports, each port is still going to be transmitting at 10 megabits per second. Hope that is very clear. This is how they are going to, this is the explanation here. A switch has 10 megabits per second, 10 megabits per second, 10 megabits per second, 10 megabits per second. But a hub here, if it is receiving at 10 megabits per second, it is going to divide that 10 megabits per second by the number of nodes which are available, such that each one of them is going to be transmitting at 3.3 megabits per second. So that is how the difference between a switch and a hub is in terms of bandwidth management, meaning that channels are going to be separated, or each channel has its own capacity, which is equal as the source channel. So these are the advantages of a switch, and then they also have some limitations. So as much as it has buffers to accommodate bursts of traffic, they can also become overwhelmed by heavy traffic, and you find that they will not be able to detect a collision when the buffer is full. And that is why we are saying sometimes there might be errors. And then we are also saying collision detection will not work since the data channels are isolated. So that is why we move to the next level, which I will show you in a while. And this is the method of cut-through switching, what I was talking about. Once it reads the first 14 bytes of a packet, then it transmits. Just here, the preamble, the ID of the packet, and the destination address. Then it proceeds. And we are saying it is faster, but it cannot detect corrupt packets. It can propagate the corrupt packets to the network, and it is best suited for small work groups. Then there is this one we are calling store and forward switching, whereby it reads the whole packet before transmitting. So it is a bit slower, but it is more accurate because it makes the use of the frame check sequence, where you can be able to check the frame and detect if there is any kind of error, and then you can request for a transmission or try to correct that error before forwarding that packet. So it is more suitable for large local area networks, and it facilitates data transfer between segments. And then they can be used to create virtual LANs, as it is shown here. That is something we can do at a higher level. And then we have routers. Routers, they operate at the OSI layer 3 of the OSI model, which is the network layer. And they use logical addresses. All these others were using the physical addresses or the frame addresses like we know them. But now when it comes to the routers, they are using the logical addresses or the IP addresses of packets and routing tables to determine the best path. So apart from just determining the destination, a router is going to determine which is the best path to deliver this packet. So that is the difference between a router and a switch. And this is how they do it. So as packets are being passed from router to router, the data link layer, source and destination address, they keep on changing, or they keep on being stripped off and then recreated. Why do they change? Because as you move from one node to the next, the source and the destination obviously may change. I hope that makes sense. Let's say, for example, you have this network again. In this network, let's say this device wants to transmit. It will transmit through this switch 1. Then it is transmitting maybe to this device. Then it will go to the hub and then to this device. So it is the work of the router to determine which is the best route. Here, you may overwork this switch, what we were calling flooding, and this hub. But when it comes to the routers, then you have to strip, because as it is moving from this is the source. When it gets to this switch, the destination, then the switch will become, in the next hop, the switch will become the source, but then the destination address is the hub, which is the next hop before you get to this destination. That is what we are talking about here. The source and the destination addresses, they keep on changing. So this enables a router to route a packet from a TCP/IP Ethernet network to a TCP/IP token ring network, because it doesn't depend on these source and destination addresses, which keep on being recreated, because these ones will be dependent on the configuration of that particular network. But then when it comes to a router, it can work in different networks. whether it is an Ethernet network and a token ring network, they will operate properly because the addresses they use, they are logical and they don't change from source to destination. So only packets which have the known network addresses will be passed. So it reduces traffic, and routers can listen to the network and identify which is the busiest path and which one is not busy, so that they can transmit the packets through that area. So this is how routing is done. A routing table will be created based on communication between routers using routing protocols. And we will see there is a chapter on routing protocols. And these routing protocols, they collect data about the current network status, and they distribute or they share with their neighbors so that they can be able to know which is the best route. And this is how they are communicating. They normally use what we call the RIP, or the routing information protocol. And there are also other protocols which are normally used. So they keep on sharing routing information so that when you want to transmit, then transmission is done quickly. This is what they use, the routing information protocol, and it normally broadcasts every 30 seconds so that it can be conveying routing information, and it can transmit this information, or it can interpret information about a maximum of 16 hops. Nowadays, it can go even beyond 16 hops. So that is one of the advantages we normally use. And if you want to check, for example, if, for example, I wanted to know where is this location, or how do I get to this particular location, then using an example, let me show you an example. This is an example of like if I want to know the routing information which is shared, and I use a simple command like a trace route. Sorry, this one is a little bit slow. Trace route, maybe google.com. Nowadays it can go up to 30 hops. So it is able to trace a route of up to 30 hops, meaning that 30 nodes along my network are able to be connected, or are able to share routing information regarding how packets are being transmitted. And this is how it does it. So from this screen here, you're able to see this is my machine and maybe a nearby switch, and then it will get us to a router somewhere which is connected to Kenneth, and another router somewhere which is CCOM again, and then another device and another node and another node. And for me to get to a Google server somewhere, I need to go nine hops, and I will get there. So that is an example of how these routers work, and they share information up to a maximum of 30 hops. Initially, it was 16. Now it is a maximum of 30 hops. So that is how routers operate. So we continue that lecture. Let me see. So that is how it works. And they share information. There is also a routing protocol example. This one is for searching for a route, whereby the open shortest path first, is OSPF protocol, is used to check. Now, if a router wanted now to transmit a packet, then it will use the OSPF protocol to know which is the shortest path to get to the particular destination which it is looking for. That is how it works. So it requires more memory. There is all this information which it requires to build a routing table. But once it has built that routing table, then it eases traffic congestion and it can go a longer path. Unlike when we have switches, which we are saying for big networks, then they become a problem. That is why we use routers. Now we also have two types of routers, whereby we have static and dynamic routers. Static routers is whereby you have to configure the routes yourself. Manual configuration of dynamic routers is done for the first route. And then after that, it is the one which continues to do automatic discovery of routes. When it comes to static routers again, it uses always the same route which you configured, but a dynamic router can select the best path or the best route depending on the network conditions. Static routers are more secure, but dynamic routers also, they require that manual configuration to improve on security. There are methods. When you go to a higher level, you'll be able to see how they are able to operate. So when we want to distinguish between routers and bridges, something I had told you we are going to look at, we are saying routers are operating at the network layer. Bridges, they are operating at the physical and data link layer. So that is one of the difference. Number two difference is that bridges, they forward everything. They don't recognize, or they cannot be able to filter information, or they cannot be able to interpret packet information to know. So they forward everything. While routers, they select the best path. Bridges operate at this layer and they always look at the MAC sub-layer, meaning that they will look at the source and the destination address, which keeps on changing. But routers, they are going to work at the layer 3 and they are able to recognize network addresses alone. Again, here, why we should use these layer 3 switches or the routers, it is explained there. Also, this is a summary of everything we have just discussed. You can look at it, and then the remote access devices like the modems, you can look at them and understand how they normally work. What we are calling the modulating and demodulating, so that we can form the word modem is explained there. And this is how the modulation is normally done. So that is all regarding the interconnection of networks and network devices.